Okay, welcome to the last talk before the keynote. And since you guys are here for so long, I don't have to talk about this because you're all excited about streaming. So I don't have to tell you about this slide. But the most important thing is streaming is a different way of thinking about processing. It's continuous and it's happening all the time. And we also need to look at all other system capabilities to make this happen well. And that's why we at Dell EMC, because we're a storage company, thought from a storage perspective, what would be the best storage solution that would make stream processing work really, really well. Today, since there is no storage system which has been inherently built for this use case, you have a mishmash of different products that are used. Some are from the messaging era, some are from Hadoop era, but all of them are not ideally suited for stream processing, primarily because there are a whole slew of newer applications like IoT and all that are coming up. Some of them need very fast small writes. Some of them need stream processing at a very high scale. And some of them really, really need to do batch processing, and some of them really need real-time applications. For all these scenarios, we thought there is a better way of doing it. And then the first thing that we're going to introduce, over the day I've heard this word stream several times. But if you look at all the products that are being used, they use either files or topics or queues, those kind of names. So the first time we're going to correct that and introduce stream as a fundamental storage primitive. What is stream? It's just stream is nothing but a continuous stream of bytes. That's all it is, right? But whether it is an IoT application which is sending small amount of data and creating millions of streams, or whether it is an application which uses a huge stream, right, and being able to scale to that, we're going to use Pravega in either cases efficiently, and that's our design goal for building it, and one of the fundamental design goals for that. Second thing is scaling of the system, right, particularly for real-time processing. The most important thing is, since they're mostly standing queries, the ability to scale the workers as the load on the stream increases or decreases is an important aspect. And then we want to cover this ground up from the storage system all the way up to the stream processors, so that in tandem they work very, very well to make this happen. That was our second design goal, which most of the existing storage systems don't do well. And finally, providing exactly once processing, which is very important. Flink does a great job in kind of doing it for a single Flink job that is running. And once the storage system is consistent and provides the exactly one semantics, it is possible to have a slew of these jobs in tandem working together, and we can provide end-to-end exactly one semantics. I think which is very, very important for us to get this right, so that, a newer class of applications can be built on top of such a storage system and with this newer stream process like Flink. And of course, we have seen this picture over today a lot in different forms. And if you look at any company's website, you'll have some form of this. The public cloud companies may be interested in furthering this because you can store in multiple places, and that's this pay-as-you-go model. You'll pay more to them and they're happy. But we are not interested in that. We want to make this very, very efficient for our enterprise customers. And we want to, and I was talking in the morning also about this. If you guys are philosophically and intellectually inclined, anytime you have more than one truth, right, which is dualism versus non-dualism intellectually always wins, right? So in our case also, we are going away from dualism to non-dualism. But if you're not philosophically oriented, if you're an engineer working on pipelines like this, you might have been woken up several times in the night because there's so many moving parts that you have to deal with any kind of Lambda architecture. So both from a storage efficiency perspective and an operational perspective, it makes a lot of sense for us to move away from the Lambda architecture to what we call a Kappa architecture. And finally, It's also that each one individually scale. The producers, whether it's millions of IoT devices or one device producing a lot of data, they have to scale independently. They have some key which makes sense for them. For example, if you're doing a monitoring application, it is the machine ID could be the key. There are a lot of these keys, we don't care. How do you partition from the producer side? What makes sense for the producer for the application? Let it use that. From the consumer side, we have a different mechanism because the processors have to deal with the range of those keys and process them effectively. And how you're going to scale in that scenario is what we're going to talk about with our new storage system. And third thing, this is I already talked about. It's not just about a single job being exactly once, but it's about combining several jobs together to be exactly once, and how a storage system in between can help to make this happen is what we're going to talk. This is one of the design goals of Pravega. And lastly, our goal in future is that we're making Pravega open source as we announced in the morning. And one of the reasons for that is we foresee a world like this where everything is built on top of streams. And then to make that happen, we want to evolve this ecosystem organically. And that's why we want to completely open source this. And we're not going to have an enterprise product and some other product, one is a cheaper version of the other, no. But the products that we're going to use is whatever we're going to have in open source, so that we can really, really build those kind of middleware on top of streaming solution that we are building on top of Pravega specifically. So with that, I talked about several things, the exactly ones, the consistency, the durability, all these properties that we want to provide with the streams, and how exactly we accomplish this in Pravega. I'll invite Tom to talk about that.
Can you hear me? Yeah. My mic is on. Okay. So Shrikant talked a lot about what we want in terms of our requirements, but the key things for us are all up here. We want data to be durable, and we want it to be durable right away. So it should be physically written to persistent media before it's acknowledged. We need to have exactly once guarantees, not just for a single reader, but for an end-to-end system. We need to make sure that it's lightweight enough that you can feel comfortable instantiating these things dynamically in your application as opposed to statically configuring them. And they should be able to grow at runtime in response to load so that things can scale up or down. And we don't want to be trapped into the capacity of a single machine. We don't want to have a case where you have to sort of have some job that reads out of this system and then writes to some other system, bringing you back to a Lambda architecture simply because you don't have the capacity in the system. We want to transparently scale for you. So to do this, we break the model of having a series of messages that are in sequence one after another, and instead we work on the concept of a stream, where you can think of Pravega as this lowest level primitive being a fancy socket or Unix pipe. This implicitly provides non-duplication and ordering guarantees, because those, if it were to violate those, that would be tantamount to data corruption. So it's completely on the client side that any higher level structure is imposed on this data. And I'll show you some examples of how we do that. So here's an example of what our lowest level API looks like. There's multiple ways to write data, but all of them are atomic. So all writes go in atomically. They're either there or they're not. And similarly on read, reads are sequential in nature. Data is immutable once written, so offsets continue to refer to the same point in data, but you can back up and read from a previous offset and resume. So that's the lowest level, but we build a lot on top of this. And the first thing we need to do is we need to figure out how to deal with the case where a write can fail due to a disconnection of the socket or server failure. And the way that we handle that is by introducing a metadata that you can attach. So it can tell the Pravega stream, okay, we're going to append this data to this stream and create this key value pair append number. We're going to set it equal to 7. And if it crashes and needs to reconnect, it can ask, what was the append number? And it can respond 7. So the client library will internally know exactly where to resume from. So you don't need to worry about retries and backoffs and so forth, adding duplicates into duplicated data. Similarly, this can easily be extended to the following feature, which you can make the append conditional. So you can say add this if the append number is less than 7 already. And this is very immediately useful as a feature we can use for deterministic Flink jobs. So if you have a Flink job and you want to use Pravega as a sink, you can have it write data, and even if it fails midway through and some of the data gets dropped and some of the data ends up in the Pravega stream, when it goes to rewrite that data, it will not be duplicated and it will automatically be deduped because of the event number. So that's one key feature. So walking through sort of the architecture of how this works internally. If you imagine we have a client here, it's connected to a Pravega server. It's going to call write, providing some data. That data is going to go its way over the wire to the Pravega server. It's going to write to Bookkeeper, which is what we use for our short-term storage for durability. Data is written there, and then once it is written to all the replicas, it is put into a local cache. Then it's another write may come in that similarly goes on the client. It's replicated to the Bookkeeper instance. It goes into the cache. And because it's not interpreting the bytes, all of that data is contiguous on the server. When a read comes in, it simply pulls the data out of the cache and returns it to the requester. When we need to evict from the cache, we just take the data that's written in these large chunks and we write them to a contiguous file in HDFS. This has the advantage that it batches all the writes together into one large write. And once that's complete, we can acknowledge back to Bookkeeper, and all of the copies of the data will be deleted from the log. When it goes to read, if the data is in HDFS, we retrieve the data from HDFS and return it to the reader, but we also prefetch and fill the cache so that future reads will come out of the cache. When we do recovery, if we have data that is in memory, that's in the cache, but is not in HDFS, a host can fail. And that data will be replayed from the Apache log, Bookkeeper log, and put on different instances. That's the only time the Bookkeeper log is read, which is very much where Bookkeeper is tuned. It's tuned for very high performance appends with rare reads. And so we're using both Bookkeeper and HDFS sort of in their sweet spot. We're using big block writes to HDFS and big block reads. And with Bookkeeper, we have these tiny appends that we get low latency on because we're not doing seeks. This results in a system where the capacity isn't constrained by a single node because you can spool to HDFS, so you're only bound by your HDFS cluster. But there's still a problem I haven't mentioned, which is how do we ensure that throughput isn't bound by a single machine? So to do that, we introduce a notion of a higher level abstraction in the client, where we let you have multiple segments as a part of the same stream. And we determine within the client library where to send data by attaching a key to it. This is a free-form string that is provided at the time of write. And you can think of that as forming a key space, which is this y-axis over on the left. And time proceeds over on the x-axis on the right. So a stream may start out with just one segment and all data ends up being written to the same place. But if the load gets too high and we decide that we need to scale up, what we can do is we can put a stop to that segment and create two more in its place. And we can scale repeatedly in this fashion. Or if we need to go down, we can end two and merge them, which is what happens there between segments 6 and 3 to form 7. So in this way, we still have the guarantees of ordering across any given key. So if you look at, like, say, in this instance, key 3, all data related to key 3 initially was written to segment 0, and then all the data following that is written to segment 1, and all the data following that is written to segment 5. So any given reader can be sure that it can get all the data from key 3 by simply following these in order. That's done all internally to the client, so the user need not be aware of it. The writers will receive an end of segment notification once the segment is terminated, and they will reconfigure themselves to work off of the new segments. Their configuration is not affected by it. So these aren't manual events that you're having to go in and redeploy your cluster or reconfigure your consumers. The same goes for the readers. This makes the event writers API looks a lot simpler right here. This is a higher level abstraction, so we are dealing with events here, but those are purely a client-side construct. And it writes the event and it gets a future back for when it's persisted. For the reader, it will receive an event that's saying, end of stream internally, and it detects that, end of segment internally, detects that, and moves on to the correct segment. And so you can see the reader API looks like this. You have a group of readers, and they're all sharing the events, and the individual events are distributed across them. All they have to do is call read next event. There's also a close method down here, which will redistribute the segments that reader was reading off of amongst the other readers. So to implement that close and to coordinate across the segments, we need a mechanism to have a common state, have shared state between the readers. And so we can use these same primitives I've already described to build something a little bit more sophisticated with one minor modification. And that's this. So as described earlier with the idempotent append, we can make something analogous that's a conditional append. You can say, I want to write this data if and only if the data would be written at this offset, where that offset is tracked from the beginning of time for a given segment. So what this does is that if there's two writers that come in and try and write the same segment in parallel, one of them will win and one of them will not. So we can take that basic primitive and abstract it to another client-level API, and that looks like this. So here we have a state synchronizer where you have this getState method that returns us a user-defined state object. This could be something like a map, a config file, what have you. It can also be membership. You can call fetch updates that will retrieve a newer state object and populate your local memory. There's also this update method, and that's where the magic is. When you call update, you provide a function that, given the latest state object, generates the update that should be applied to it. And it's guaranteed that that update will only be applied if the state object that it was applied to was the latest one, and that using optimistic concurrency. So that function may be invoked more than once if you have contention, but eventually the update will either be generated and applied, or the function will decide that their update shouldn't be applied. So this gives you a very strong synchronization primitive, and that's exactly what the readers use to coordinate amongst themselves. This is quite a large departure from APIs you've seen in perhaps other systems, but I think that this sort of API is the sort of thing that's going to be possible with this sort of low-level streaming primitive, and I envision a lot more APIs that are either like this or quite different, but similarly divergent to appear in the future. So an example of what you really want to be able to do, and what we can do with this API, although it's not obvious, is transactional output. We would like to be able to have one Flink job put output somewhere, in this case, Pravega stream, and have another Flink job be able to read that data with exactly once guarantees end-to-end. And today, that's only possible with batch mode writing to something like HDFS, where you have the ability to have the HDFS transactional output that the Flink authors have created. What we really want to do that is on a stream. So this gives you the advantages of idempotent output, but without your job having to be deterministic. So if you'll notice the writer API, we have this API at the bottom there called begin transaction, and that's exactly what that does. A transaction looks a lot like an event writer. You can write events to it and call commit or abort, and all the events that were written will either be committed atomically or aborted, and none of them will exist. The way that works on an individual segment level is as follows. A segment can be continued to be written to and appended as time goes on. But once you can decide you want to start a transaction, what actually happens is it creates a new segment, because segments are extremely cheap and the data is written there. And once commit is called, that data is, through a metadata operation, merged into the parent segment from which it came, at which point data can continue to be appended to the original segment. So this is a very cheap operation because the merging is strictly a metadata call. But we want to do more than just one segment. We want to do segments across the entire stream, because we want to be able to allow streams to scale. So we can do that as follows. We can use the state synchronizer mechanism in a separate process that we call the controller, which operates as a sort of a transaction observer. And what you do is you call it and tell it to create a transaction for you. And it does so. And then the writer can begin writing to multiple different segments in parallel. And then when commit is called on the controller, it'll be committed on all the Pravega segments. And the controller will ensure that either all of those go in or none of them do. So this expands the power of transactions and lets you do something like this, which is even more sophisticated. Because that mechanism was built using just the state synchronizer and the other primitives I've already described, it's not limited to being on the segments of a given stream. It can actually operate across streams. So here we have an example of a Flink job where it's writing to two separate Pravega streams, and those two transactions are combined atomically so that their results are only visible together, and a downstream Flink job can depend on both. But this isn't where this ends. You can actually introduce an external dependency and key the transaction's commit or failure based upon that. So here we could have an external data store. It could be, for instance, Flink's checkpoint store. It could be a SQL database that you output to. And then if and only if the data is written and committed to that store, do the transactions go through and the data moves downstream. This provides an even stronger semantic, and it's still built on the same primitives that I've already described. So this is something we're really excited about. We think it greatly expands the capability of what you can do with streams today, and it's a very efficient primitive, and we are really excited to unveil it. And so that's why May 10th, we're going to be opening up our GitHub repo to the public, and we look forward to all of you joining and becoming committers. We do have a booth. If you haven't been there already, you can come talk to us, or we also have an email that you can send if you have questions or comments.
Yeah, just to conclude once more, right? First of all, as I started the conversation aside, we have different storage systems that are available already. And this storage system we have reimagined specifically to work with stream processors like Flink, right? How did we do that? First thing, small writes, it'll work well because we append to Bookkeeper and then ACK them back. They're durable because without replicating them, we never ACK anything. They're consistent because we strongly guarantee the order, even if you don't use transaction. And top of it, we provide transactions to provide consistency across different jobs. And as Tom just explained, the transactions are not within a segment, not within a stream. You can do across streams also. And we support all those mechanisms in this, right? And finally, with stream is infinite. So remember the non-dualism versus dualism thing argument that I had? Stream is infinite, means you can always go through Flink's real-time jobs or real-time processing or batch processing through the same abstraction of a stream. Because for the catch-up reads, it's a bounded data that you can pull from HDFS, which is very good for that. And then you can do, and for real-time jobs, you're pulling from the cache, or if it is already in the HDFS, you can pull from there and process it, right? And finally, because of the way the segment is a two-dimensional thing, as time goes, we split and merge the segment as we go. Because of that, we're going to automatically scale the Flink job or the Flink workers based on the number of segments so that you don't have to really do anything for that. And since we're working with the Flink guys, we're going to have the connector so that this all works seamlessly. And then you can then orchestrate with any of the famous orchestrating mechanisms like Mesos or Kubernetes, whatever you have. So that end-to-end, this whole thing will, the real dream of any stream process like Flink is to provide you the ability to do both batch and real-time on the same thing, and the ability to kind of scale automatically, and the ability to write stateful applications without worrying about a machine going down or anything like that. In all those scenarios, we try to cover with Pravega as the storage underneath. And any questions?
In the back.
Yeah.
The consumers within, we have a notion called a consumer group. Okay. The question is, how do we ensure that multiple consumers, when they're reading from the stream, don't consume the same data? And the answer is we have a notion called a consumer group, where consumers, when they go to consume from a stream, they join a consumer group, and that group has a state synchronizer, and they coordinate them amongst themselves using that mechanism. So they have consistency, and they have agreement amongst each other as to who's reading from what segment at any given time. Yes. So I'm not sure I understand the question. No, Pravega does not have any dependency on the database. So the question is, if you're using Pravega to write data transactionally to Pravega and to a data store, what you're gaining is the ability to write. We don't know or care what your database is, but what you are gaining is the ability to write to two places atomically. The question is about ordering guarantees within consumer groups. So if you're operating a consumer group, the stream looks something like this, and different readers will be reading from different segments. So at time T3, for instance, you might have as many as 3 readers, and they might be reading in parallel from segment 5, 6, 3, and 4. And if and the readers in segment 5 are receiving all events related to the keys that are in the key range between 2 and 3 up there at the top, and so they will receive all data for that in order. And if segment in the past, when segment 1 ended and the reader that was reading segment 1 finished, it is only after segment 1 finished that anything from segment 6 or 5 should be read, because everything in segment 1 by definition comes before everything in segment 6 and 5. So you still get ordering guarantees. It's just that you can only start reading from segments once the reader has finished their predecessors.
So one important point I think we should mention is that a segment can be split as small as one key. That's all. It can't be smaller than a key. In general, a segment is a range of keys. The smallest it can grow is this, and the biggest it can grow is the full range of keys that you have. So unlike systems which do static partitioning, in our case, the producers, based on their business needs, can choose whatever keys. There is no restriction amount of keys. And the consumers basically vary up and down based on the range of keys that they're going to consume. And we are going to do the split and merge automatically in Pravega based on the amount of data coming in. So that's how it's going to work.
The question is, do we make split and merge decisions based on read load? The split and merge decisions are at the moment configurable based on rates. We are open to adding more policies, but that's how they're done today. The rate of writes at the time the split or merge occurs.
I can have parallel writers to a single segment, right?
Correct.
And you have the synchronization primitives that you described before. How do you prevent starvation if I'm racing writers and they both try to use the same offset, only one wins?
Right.
Each writer potentially needs to know what offset it wrote to.
Okay, so the question is, in this scenario, can you have starvation? You can definitely have contention in this scenario if everyone's making their offsets, their rights conditional. Under most circumstances, you don't necessarily make your rights conditional. You would make your rights conditional if you're using an API like this, where you're doing an update state, and you want that right to fail if somebody else has modified the stream. In which case, you're limited to any optimistic concurrency system is going to have the same drawback. If you have many people trying to contend on the same item, you're going to slow down, but one of them will succeed in each round.
But there are systems that allow you to give everybody a chance to run.
Certainly, you could pessimistic concurrency systems work better when pessimism is justified. Optimistic concurrency systems work better when optimism is justified. So this API works better when optimism is justified. But this is not what you would do if you wanted to write a stream contiguously at high throughput. Your rights would not be conditional.
So there are no benchmarks yet. We don't release this at this point of time. But one of the design goals we have is that the ingestion rate at the input should be very fast. And our goal is to be under 10 milliseconds there. And we think that we're going to achieve that, primarily because of the way we write. Unlike several other systems where they're writing and reading from the same place, resulting in contention between readers and writers, particularly for something like a stream. If you're writing at the tail end, the tail write should be fast. At the same time, the reads are happening at different positions in the stream. If you're writing to the same place, then there is obviously a contention between those two, and there will be performance issues when you have multiple readers reading from different offsets. In our case, because we are constantly splitting them into segments and moving into different machines, what will happen is there will not be contention, and the read path and write path are different. Because of these reasons, we are more efficient for both tail reads, tail writes, and catch-up reads, right? And that's why it works both for real-time processing and batch processing as a storage system. They don't do that. Right.
The question is transaction server or the controller. There are multiple instances of the controller. It doesn't need to be a single instance. So you can spread its job across as many hosts as you need.
Yeah. First of all, transaction server is a bad word, so let's not use that word. so this is a Pravega controller, which is completely stateless set of machines to which it goes, and it's backed up by consistent store to support it, right? So that's how it scales.
Right. So the question is essentially how thick or thin are the clients, and how easy is it to create a new language. So the lowest level client is very easy to create, right? The lowest level client where you just write in bytes and those are atomic. But we end up doing a lot of things on top of that in the client, and those are more complicated and will take more time to implement in other languages. So I expect it will perhaps take longer to get fully fledged complex clients in different languages, but the very simple clients that just write bytes to a stream will be easy.
So you said it's up to the client to understand the message format. So it's up to the client to make self-check summing messages and understand message boundaries.
Yes.
You don't do any of that?
The server does not do anything. Correct.
So even if there's a corruption in SSDs, you won't detect it?
Correct.
And so it's up to the client to discover that client's got to run FISC, that message. They got to implement their own.
Bookkeeper provides its own checks. HDFS provides its own checks. We aren't doing anything above and beyond what they provide.
Yeah. Yeah, it's conceptually bytes, right? But the storage system, when you write, obviously there are checks and balances there to kind of make it happen. Yeah.
How do you actually organize them internally?
Where?
You have multiple pieces of segments chained together, and you start with this segment, so you also need to keep track, when a segment gets split, then you have to look up and what segment key is in time, so not metadata anymore.
Yes. So here's a good picture to illustrate. When you have multiple segments, they are in the bookkeeper. They are all interleaved. They're all writes in the right order. So bookkeeper is a log, and that's where it has the highest performance. That's how we can get such low write latencies. In HDFS, they're written out independently. It's by segment, and that transition occurs when we do eviction. So we are holding the data up here in our cache in by segment, and then when we need to evict from the cache, we're writing it out in a big chunk to HDFS. So to HDFS, you get your data organized by segments, which is very convenient for reads. And when you're writing it, you get it all interleaved to Bookkeeper, which is very convenient for writes.
So in short, actually, what he's trying to say is that when in Bookkeeper, since they're all interleaved, you kind of combine a bunch of segments into one container kind of thing and write into a single journal there. So it's not much of a thing. On HDFS, a segment is equivalent to file. So whatever bookkeeping you do for a file in HDFS, the same thing. Same overhead. Yeah, good.
In the context of large messages, if something doesn't fit the network packet, there are times when I don't get all of the right.
Right.
And the server has to decide whether to declare that message is never going to happen, or you get basically headline blocking for everybody else.
Events going into the server, one writer will never block another writer. So if a writer sends half of an event and then never finishes it, he's only blocking himself. If he disappears, he disappears.
But you got to clean up that stuff eventually.
Yeah. In the back.
So when you're writing for single stream, you're using Bookkeeper, it's true that you never see it all, right? You never have to see it.
Regardless of the number of streams, yes.
Not that I can ask. Is it
Regardless
regardless of the number of streams?
of the number of streams.
Then the right path is everything else.
Correct.
Okay. So one last question.
Do you have an example of it when you have to get the
So do you have an example of what? I didn't understand the question. Right. See, once we have this Flink connector written up, any job, right? Now, today, Flink jobs have static number of workers, right? So that they will scale up and down automatically based on the number of segments in the stream. That's our goal, and we are working with the data artisan guys to get that done. So it'll work with this in tandem. So I think we have run out of time. I want you guys to check your lady luck. So I invite Priya to kind of draw for the, what's this called?
The BB-8 robot.
I'll read for you. Oh, this can write to Pravega. All the events it can send to Pravega.
Clip art.
There you go.